So in this video right here, what I'm going to talk about is how to calculate essentially the pH required for essentially an acid-base reaction to eat up in a way a common ion in this case. So the problem right here, right, is like calculating the concentration of magnesium 2+ in seawater. Right, if it starts off at 0.052 molarity, right, in seawater, if you're trying to remove 99% of the magnesium 2+ ions, which as somebody who has a reef tank and has corals and fish is not a good thing, right? They actually need the magnesium, and so you have to be very, very careful with your pH. But if you wanted to hypothetically remove 99% of the magnesium ions out of your solution, right, what pH would you have to be at in that case? And so, when you're going to a lower pH, you start to have more and more hydroxide ions, and hydroxide ions in many cases are insoluble, right? So they're really only soluble with first row alkali metals. Magnesium hydroxide readily precipitates out, and so we have we can see that right here from the solubility product that we have for magnesium hydroxide, which is 8.9 times 10 to the negative 12, right? So that's a not very soluble salt in this case right here. So the question is, how do we approach this problem? So first things first, right? If we write out what the equation is for the reaction, right? We have magnesium hydroxide in this case, right, as a solid, right? And that's going to be forming magnesium 2+ aqueous plus hydroxide ion aqueous, right? And it's going to form two equivalents of the hydroxide ion. So that right there is our KSP. Right here, right? And so that from that equation is 8.9 times 10 to the negative 12. And so if we write out what the expression is, right, it's the concentration of magnesium 2+ times the concentration of hydroxide ion squared in this case. So now the question is, well, what values do we have in this case right here? So we know that starting off that we're at 0.052 molarity, but we want to remove 99%. So when we're after removing 99%, right, the question is, what is the concentration of, the magnesium then at that point? And so if we're starting off, magnesium 2+, right, the initial concentration is 0.052 molarity, but if we only want to have essentially 1% of that remaining, we just multiply that by 0.01. And so what we get is that the concentration should be 5.2 times 10 to the negative 4 molarity in this case right here. Right? And so that's going to be then what we're going to be using for our equation. So if we look up our if we set our ice table in this case, or actually, sorry, we don't have to set up an ice table. I'm going to delete that. Right, so we have the concentration right here. So now what we want to figure out, right, is what the concentration of OH minus is in this case. So all we have to do is we can rearrange the KSP expression so that what we have is the concentration of OH minus is going to be equal to KSP divided by the concentration of magnesium 2+ at the concentration that we're at. And that's then going to be to the power of 1/2, right? Because that's going to remove the squared. We can also do right square root, right? That's another way that you can refer to it as. So we have this right here. So if we plug in our values, I'm going to do it right here because there's more space, right? So what we have is at the KSP is 8.9 times 10 to the negative 12, right? The concentration of magnesium that we have that we calculated that we want to be at this point is 5.2 times 10 to the negative 4. And then that, right, is going to be the square root of that. And so we calculate all of that out. What we get then is that the concentration of hydroxide ion at that point is going to be 1.31 times 10 to the negative 4 molarity, right? So now we know the concentration of hydroxide ions. We can easily figure out what the pH is. So to do that, the easiest way, in my opinion, to do that is first to calculate what the pOH is, right? So the pOH is equal to the negative log of the concentration of hydroxide ion. And so if we plug in what we have, the negative log of 1.31 times 10 to the negative 4 molarity is 3.88, right? So that's the pOH. And so the pH, right, to calculate that is just simply 14 minus the pOH, So if we have 14 minus 3.88, what we get is that the pH is going to be 10.12, right? So if you raise the pH of seawater to 10.12, you start to precipitate out most of the magnesium hydroxide, right? And so that's a really important thing to think about, is that, in oceans and everything like that, the pH is extremely important, right? You don't want it to get too low because then, things start to precipitate out. Life doesn't really like that. And then, right, you also don't want to go in the other direction where you start to be at a really low pH because things then start to dissolve that you don't necessarily want to have dissolved. So there's always a delicate balance in those cases. But this is how you approach this this type of problem, right? So you can calculate, if you know what the concentration is of something, of one part of the solubility product, right, you can easily figure them out. What the other one is if you then know the KSP.